It's important to note, guys, that this only works when these bases are the same. Okay, I haven't written it in here, so of course I'm using base 10. Okay, but this only works, this rule only works when you're taking the same base of logarithms. Okay, if you don't take the same base, you can't apply these rules. Okay, because everything we've just done up here doesn't apply. Okay, next rule. So the quotient law. We're going to determine an equivalent expression for log base A m divided by n, where a, m, and n are positive numbers. Again, starting positive, and a can't be 1. Alright, so we're going to go through the same process here. We're going to let m be base a raised to x, and n be a number that's base a raised to the exponent of y. Okay, now we do the same idea. We substitute that into the quotient, and we get ax minus y. So log a m over n is equal to log a base a x minus y as the exponent. Okay, this is the exact same process we used with the multiplying. So therefore, this term is equivalent to x minus y. Who can tell me why? This is the same thing again. Who can just tell me why that is equal to that? This is the basics, right? The whole understanding. Yeah, Ramon?
The exponent that a needs to be raised to is x minus y.
Yes, the exponent that a needs to be raised to get a to the exponent x minus y is, of course, x minus y. Right. Okay, you need to understand that. Might not kind of seem important or relevant now, but when you're working on word problems that, that's going to come up quite often, that you need to understand how this goes to there. Okay? Any questions? All right, so if that's the case, now we sub back in these values for m and n, these two values, and then we take the logarithm and find that log am is equal to x and log an is equal to y. This is exactly from the previous law we built. Sub those two values in for x and y, and we get this result. So here's your second law. When you have two unknown numbers or two variables divided that you're taking the logarithm of, you can then separate them and subtract them. Okay? So this is really a big advantage for logarithms, and kind of almost the point of why we study them is because of this ability, and these laws in particular. They allow you to isolate and find unknown variables in the exponents without doing guess and check, and without having to try to find the same base, right? That's our other option, is where we find the same base and then relate the exponents. It's not always easy to find the same base if it's not an even number, okay? So that's what this is allowing us to do, these rules, okay? All right, example 3. So this is going to be a quotient example. Oh, no, sorry. This is going to be the third law, the power law, okay? Determine an expression for log base a m to the exponent of n, where a, m, and n are positive numbers and a cannot equal 1. Same rules apply. So we do those same substitutions. We use the exponent law here. A to the exponent of x raised to the exponent of n is a n x. Once we do our substitutions in here for m raised to n, we get log a n x. So this goes to this based on the exact same reason. What is the power that a needs to be raised to get a to the exponent of nx? Well, it's nx. Now we substitute in the value of x, log base am, and we get this result. So what you notice is, from the original question, we notice that if here's our original logarithm, we notice that we can drop the exponent down in front of the logarithm. So that arguably may be the most practical law of logarithms, is if you have a log with a power, you can take the exponent of that power and drop it down in front. Okay, so that m that was raised to n, the n came down in front. Okay, and here's the proof for why you can do that. Any questions there? All right. So A, which exponent law is related to each logarithm law? How can this be seen in the operations used in each pair of related laws? All right. So the first one is our product law. We call it for exponential terms. So we know that that's the law. A raised to the exponent of x times a raised to the exponent of y is ax plus y. Our logarithm law that goes with that exponential law or product law is this. Okay, so where we have m and n in brackets, we can now separate them, adding an addition between those two logarithms. Okay, that's the first one we covered. Second one, our quotient law with exponential was we could subtract the exponents of two powers that were divided. That allows us to, when we take a logarithm of a quotient, we can separate the numerator and the denominator by taking the logarithm of both the numerator and denominator and subtracting them. Okay, obviously the numerator comes first. The power law is a power raised to an exponent. That allows us to drop that leading exponent down. So here n can come in front of n log m. Okay? They become a lot easier and useful once you get some practice using them. Why does it make sense that each exponent law has a related logarithm law? So given the fact that logarithms are exponent, it stands to reason that the laws of exponents should apply to logarithms, right? They're inverse of the exponential functions, so those same laws should apply. Finally, the last two questions, it says, can log base 2 5 plus log base 3 7 be expressed as a single logarithm using any of the logarithm laws? Why not? Right. Okay, so I mentioned it earlier. If these bases are not the same, you can't use any of these laws. Okay, you can't use them to combine terms, you can't use them to separate terms. Okay? Finally, the last question is the same. Again, base 6 and base 4, can they be used? No, they can't. Okay? Alright, a couple of quick examples. It says simplify each logarithmic expression. So we have log base 3 6 plus log base 3 4.5. So here's our law. We're going to go in reverse now though. So we're adding two separate logarithms. We can put them in brackets and multiply them with one logarithm. So we get log base 327. Okay, so very simple. We can solve that.
How do you go from log 327 to 3?
What is, okay, so this is an exponent. The result is an exponent. It's an exponent that 3 needs to be raised to get 7. It's 3, okay? All right. Log 2, base 2, 48 minus log 2, base 2, 3. We can now divide those two terms because we have a subtraction there. We get log 2, 16, which we know is 4. 2 needs to be raised to 4 to get 16, okay? Finally, the last one, we have a cubic root. So we have log base 5, 25 to the cubic root. So we can drop that exponent down based on our power law of logarithms. So that comes down. So we have 1/3 log base 5, 25. We know that 5 needs to be to the exponent of 2 to get 25. So log 5, 25 is 2. And so we just do 1/3 times 2. So we get 2/3. Example 5. It says graph the function log 1000x and gx equals 3 plus log x. So be careful here. Realize that there's two terms here. There's 1000 and there's x. Okay, so we can actually separate those two terms based on what we've learned now. This is 1000 times x, right? It says how do the graphs compare? So what they find is when they graph them, they get identical graphs. Okay, the graphs are exactly the same for this function and this function. So we need to discover why. So what we do is we take one of the functions, log 1000x, and we apply our logarithms law. So log 1000x, we can separate that into log 1000 plus log x. Log base 10 of 1000 is 3. 3 plus log x, we have the other function. Okay, so that's why they're the same. Here's our other function. This is the last example. So it says use the properties of logarithms to express, and this looks very complicated, okay, but it's not bad once we apply our logarithm laws. So the first thing we'll want to do is we'll take that square root and express it as an exponent, okay? What that allows us to do is we can now drop that exponent down in front of the logarithms. Okay, and then we can start to work on the inside of the brackets. So we do that, we drop the half in front. Now we take this, which is a quotient, and we subtract log of the numerator minus log of the denominator. Okay? Now we have 1/2 times these values. We can take this term, which again is a product, and we can separate it into log x to the exponent of 3 plus log y squared. Okay? See how we separated that to those two terms. Next, we can now multiply, just like we would with any other trinomial. We would multiply it by what's in front of the bracket, so that half goes to each term. So it becomes 1/2 log base a x cubed plus 1/2 log base a y squared minus 1/2 log base a w. And finally, we can use the power law again and start dropping those exponents down. So the 3 comes in front of the half, log a x plus 1/2, that 2 comes down, and the w stays. There's no exponent to lower, so that stays the same. And now we just do those simple multiplications in front, and we end up with our final answer. Okay, so that's a simplified expression of this. Okay, so the key idea, the laws of logarithms are directly related to the laws of exponents, so logarithms are exponents. The laws of logarithms can be used to simplify logarithmic expressions if all the logarithms have the same base. That's important. If. And finally, the laws we need to know is the product law of logarithms. When we have two numbers multiplied, or the product of two numbers, they can be separated by addition. When they're divided, or a quotient, they can be separated by subtraction. This is important, right? This order is important. For here it doesn't matter which one you put first to add. Here it does. You have to put the numerator first. Okay? And finally, the power of the logarithms, you can lower that exponent. That exponent comes down. All right.